Hello everyone. In today's lecture we will continue working on the Z transform. In this chapter we have learned what is a Z transform and we have seen it as a tool that can be used to deal with discrete time signals and discrete time systems. We have learned how to compute the Z transforms, the region of convergence, how to find the location of poles and zeros, and we have learned the importance of the location of poles and zeros and how they affect the frequency response of a system. Today we will start with the inverse Z transform. In the inverse Z transform we have the function x of z and the region of convergence, and we will need to find the discrete time sequence x of n. The formal definition of the inverse Z transform involves a complex integral over a closed contour in the Z domain. This complex integration can be performed using the residue method, which is quite difficult to perform. However, there are simpler procedures which can be used and are sufficient for most practical cases. For most practical cases, x of z takes on a certain form, that is a rational function, that is a ratio between two polynomials. In this case, if x of z is a ratio between two polynomials, now we have simpler procedures to follow. These procedures basically are as follows. First step, we can expand x of z as a series of terms in the variable z and z minus 1. In this case, we can do the inverse right away. The inverse of z minus 1 is delta of n minus 1, and inverse of z is delta of n plus 1, and so on. In order to express x of z as a series of terms of this form, we can use the long division, as we're going to see later on. The second step is to do the partial fraction. If we can transform this rational function using partial fraction into simpler fractions, then we can use the lookup table we have built during the previous lectures to do the inverse transform. So the idea is simply like this. If we can express x of z, which is a rational function ratio between two polynomials, and these polynomials are in the variable z minus 1. If we can expand this rational function as a summation of simpler terms like this one, constant over 1 minus the pool pk times z minus 1. This term can be inverted or can be transformed back into time domain right away. If we know that the region of convergence is going outward, so the corresponding discrete time sequence will be right-sided, and the term will be the pool pk to the power n u of n. And if the ROC is going inward, in this case the term in time domain would be left-sided, and it will take the form pk to the power n times u of minus n minus 1. So doing the inverse here is much more easier than using the formal definition, which involve a complex integration and using the residue method. So all the problems we're going to deal with here are basically of this form. X of z is a rational function. We will do a long division and or partial fraction in order to get x of z in this form, and then we can do the inverse transform for every term, and then we can add the terms together. Uh, don't worry too much about this slide. This slide is simply saying that if x of z is a summation of these simpler terms, we can get a common denominator and simplify the terms, and we will get this kind of expression, a rational function, ratio between two polynomials. The numerator here is a polynomial of the variable z minus 1, and the denominator as well is another polynomial of the variable z minus 1. So x of z being a ratio between two polynomials, we call it a rational function. And this rational function can be expressed in this form as a summation of simpler terms. And the way we're gonna do it is using the partial fraction. Partial fraction will help us to move from this expression, rational function, to this expression. Okay, so in order to wrap things up, in order to perform the inverse Z transform, we need to do the following. First step, if the rational function we have is proper, and by proper we mean that the order of the numerator is less than the order of the denominator. In this case, we can use the partial fraction right away, and then we can use the lookup table we have built in the previous lectures. But if the rational function is improper, and by improper we mean that the order of the numerator is larger than or equal to the order of the denominator. In this case, we first need to do the long division, and then we need to do the partial fraction and the lookup table. This is to remind you with the partial fractions, if the factor in the denominator takes the form ax plus b, the corresponding partial fraction is constant over ax plus b. If the term in the denominator is ax plus b to the power k, the corresponding partial fraction terms would be constant over ax plus b plus a constant over ax plus b squared until we get a term constant over ax plus b to the power k. This k is equal to this k. Okay, so now we have an example. We're asked to determine the time domain sequence x of n whose z transform is given by x of z equals this function. This function is basically a rational function. It is a ratio between two polynomials. The polynomial in the numerator is of the first order, and the polynomial in the denominator is of a second order. So it's a proper rational function, and we do not need to do the long division, we only need to do the partial fraction. So doing the partial fraction, we need to expand or factor the denominator into first order terms like this one. So it can be easily seen that this quadratic term can be expanded as 1 minus z minus 1 times 1 minus half z minus 1. Of course, this factorization can be done easily here, but if not, you can use your calculator, or you can use a famous equation for computing the roots of a quadratic equation. This equation takes the form 1 over 2a times minus b plus minus square root of b squared minus 4ac. It's kind of famous equation you have seen in math. Anyway, doing the factorization, we realize that here we have two pools. One pool is located at half, and the other pool is located at 1. The pool is a constant being multiplied by z minus 1, in this case 1, and here it's half. So this x of z has two pools. And in order to do the inverse z transform, we need to know the region of convergence. But as you can see in this example, the region of convergence is not given. That's why we will need to solve for all possible region of convergence. So let's try to find out what are the possible region of convergences. Now that we have a pool at 1 and another pool at half, we have actually three possible region of convergences. The first region of convergence is inside the circle whose radius is half. In this case, since the ROC is going inward, the sequence in time x of n would be a left-sided sequence or an anti-causal sequence. The other possible region of convergence is outside the circle whose radius is 1. In this case, the corresponding sequence in time would be right-sided sequence or a causal sequence. The third possible region of convergence is in between the two circles whose radiuses are half and 1. In this case, the sequence in time x of n would be a two-sided sequence. So now that we know the possible ROCs, we will solve the problem 3 times for the 3 possible regions of convergence. So since x of z is a proper rational function, we can do the partial fraction right away, and we can write it as a constant over the first factor here, which is 1 minus z minus 1, plus another constant over the second factor here, which is 1 minus half z minus 1. And of course, the constants a1 and a2 can be easily computed, as we have seen in mathematics and as we have seen in the previous lecture. It's simply a1 times 1 minus half z minus 1 plus a2 times 1 minus z minus 1 equals 1 plus z minus 1. And then you substitute z for 1 and half, and you get the values right away. So we will get a1 equals to 4 and a2 equals to minus 3. Now we're ready to do the inverse transform. So for the first region of convergence, ROC1, for which modulus z is less than half, this region of convergence is this one, which is the interior of a circle whose radius is half. If we take a closer look here, for the pool half, the ROC is going inward. Hence, the time domain sequence would take the form half to the power n u of minus n minus 1. And for the pool at 1, this ROC is also going inward. In this case, the corresponding term would be 1 minus 1 to the power n times u of minus n minus 1. The two sequences would be left-sided. So it would be like this. The 4 is a constant. It goes down like the same way. And 1 over 1 minus z minus 1, this will give you the pool, which is 1 to the power n times u of minus n minus 1 with a negative sign. We got this from the lookup table we have built in the previous lectures. Same way here, the minus 3 goes down as is, and then we have a term 1 over 1 minus half. Z minus 1 half is the pool, so the term in time domain would be half to the power n times u minus n minus 1. We have chosen the sequence is to be left-sided because ROC is going inward. Moving on to the second region of convergence, ROC2, which is in between the two circles, one at half and one at 1. Let's go back here and take a closer look. So this is the second region of convergence. For the pool at half, the ROC is going outward. So the term corresponding to the pool half should be a right-sided signal. So for the pool half, the term would be half to the power n u of n. Whereas for the second pool, which is located at 1, the ROC is going inward. In this case, the term should be 1 to the power n times u minus n minus 1. And we can see it clearly here that for the pool located at half, it would be half to the power n u of n. And for the pool located at 1, it would be 1 to the power n u of minus n minus 1. And as we can see, the sequence in time domain is two-sided. This term represents a left-sided sequence, and this term is a right-sided sequence. So in overall, it's a two-sided sequence. The third region of convergence, which is modulus z larger than 1, if we go back to the figure here, if modulus z is larger than 1, then the ROC is going outward for both pools, and hence the terms would be half to the power n u of n and 1 to the power n u of n. So as we can see here, x of n would be 1 to the power n u of n and half to the power n u of n. This example actually is really simple, but it helped us to learn how to do the partial fraction and how to find the possible region of convergences and how to compute the x of n, the discrete time sequence. Another example here, and we're asked to determine the causal sequence x of n whose z transform is given like this. Before we go on here, let's take a minute and think about this part, the causal sequence. For a sequence to be causal, it has to be right-sided. So we are given that x of n is a right-sided sequence, which means the region of convergence must be going outward. So when the question asks you for the causal sequence, it is simply telling you solve only for the ROC which is going outward, as if it's actually specifying one ROC which we can use in our solution. Okay, so x of z is a rational function. It's a proper one. The numerator is of order 1 and the denominator is of order 2, so it's a proper rational function. And we need to factorize the denominator. We can use a calculator in this case, and we will get the pools to be complex pools. One pool is located as half 1 plus j and the other pool at half 1 minus j. And as you can see, the pools are complex conjugate. Pool 2, P2, is the conjugate of P1. So we will have this form 1 minus P1 Z minus 1 minus P2 Z minus 1. These are the two pools. Of course, in order to obtain P1 and P2, you can use your calculator, or you can use a formula for computing the roots of a quadratic equation. In both cases, there is a trick, there is a problem that usually students make in performing or finding the roots here. Uh, in the quadratic equation we are used to, it takes the form ax squared plus bx plus c equals 0. So the variable actually is x or z, whereas here the variable is z minus 1 in our case. So if you're using your calculator, you will be asked to enter the constants a, b, and c. If you choose a to be half, and b to be minus 1, and c to be 1, in this case you're solving for the variable z minus 1. And the calculator will give you the roots of the variable, for the variable z minus 1. So the values you will get from the calculator is actually the inverse of this one and the inverse of this one. If you want to get these pools right away, multiply the whole denominator by z squared, so you will get a polynomial of this form. Z squared minus z plus half equals 0. In this case, a equals 1, b equals minus 1, and c equals half. And in this case, the calculator will give you the roots for the variable z, which is what we're looking for. So now that we have found the pools, x of z will take the form constant over 1 minus p1 z minus 1 plus another constant over 1 minus p2 z minus 1. This form. And since P1 and P2 are complex conjugate pools, also A1 and A2 will be complex conjugate to each other. So computing A1 and A2 in a similar manner as we have done in the previous example, A1 will be half 1 minus J3, and A2 will be the conjugate of A1, which is half times 1 plus J3. So now we are ready to do the inverse Z transform. This term will be inverted like this. A1 goes as is. Since we are asked to find the causal sequence, so the ROC is going outward, the sequence is causal, ROC is going outward, modulus Z should be larger than modulus P1, which is 1 over square root of 2. So the sequence in time will be right-sided. And the inverse of this term would be P1 to the power n u of n, and the inverse of this term would be P2 to the power n u of n. And if you remember an example we have done in the previous lecture where we had x of n equals cosine omega n u of n, a cosine wave. And when we did the Z transform, when we found Z transform, we got two pools, and the two pools were complex conjugate pools. So now that we have a complex conjugate pools, doing the inverse transform, we should expect x of n to take the form of a cosine or sine wave. So a general note here is that in Z transform, if you get a complex conjugate pools in Z domain, probably you will be getting a sine or cosine wave in the time domain. So here we will express the pools P1 and P2 as magnitude P e to the power j omega node and P e to the power negative j omega node. We will also express the constants A1 and A2 as magnitude A e to the power j theta and A e to the power negative j theta. As you can see here, P1 and P2 have the same magnitude, but the angle in the exponent here only differs by a negative sign because they are conjugate. When you conjugate a complex number, you change the sign of the imaginary part or whatever is beside j. Same for A1 and A2. So Starting from the expression we found here, if we replace a1 with a e to the power j theta and p1 with p e to the power j omega node, same for a2 and p2. Now we can take a as a common factor, p to the power n as a common factor, and we will get this term, e to the j theta, e to the j omega node n. And here, e to the negative j theta and e to the negative j omega node n. If you combine these two exponentials together, you will get e to the j omega naught n plus theta, e to the negative j omega naught n plus theta. And these two complex exponentials added together will give us 2 cosine omega naught n plus theta. So we found actually was what we have been saying a few minutes ago, that having complex conjugate pools usually will get a cosine wave in the time domain. Okay. Another example, we're asked to determine the sequence x of n whose z transform is given by this rational function. And I guess we have already done this example in the previous lecture. We will go over it quickly, but we have done it in details in the previous lecture. So this rational function is improper because the polynomial in the numerator is of order 2 and the polynomial in the denominator is of order 2. So it's improper rational function. So we should first start by doing the long division in order to convert it to a proper rational function, and then we can do the partial fraction. Doing the long division, we have done it in the previous lecture, and we will get this kind of term, 1 plus a rational function, and this rational function is now proper. The order of the numerator is 1, the order of the denominator is 2, so it's a proper rational function. So in order to do the partial fraction, we need to factorize the denominator, and here it can be done easily or use your calculator, it's up to you. So it's 1 minus 2z minus 1, 1 minus z minus 1. Okay, and here, since the question did not specify a certain region of convergence, we need to find all possible region of convergences and solve in all possible ROCs. So we have here two pools. One pool located at 2 and the other pool located at 1. So we will have three possible region of convergences outside the circle whose radius is 2, between the two circles whose radiuses are 1 and 2, and inside the circle whose radius is 1. So doing the partial fraction, we have a constant over 1 minus 2z minus 1 plus constant over 1 minus z minus 1, as the constants can be found easily. We have done this before. Since no ROC is specified, we need to solve for all possible ROCs. So the first ROC is if modulo z is less than 1. So inside the circle whose radius is 1, in this case the ROC is going inward, and the sequence x of n should be left-sided. Okay, so the first term in x of z was 1. The inverse of 1 in z domain is delta of n, because 1 is actually z to the power 0. So it can be inverted as delta of n minus 0, which is delta of n. And then we had a pool at 2. The corresponding discrete time sequence would be 2 to the power n, u of minus n minus 1, and we have chosen the left-sided sequence because ROC is going inward. Same here for this pool at 1, it will be 1 to the power n, u of minus n minus 1, because it's a left-side sequence. So here we can see it clearly. So the 1 is inverted to delta of n, and the pool at 2 is chosen to be 2 to the power n, u of minus n minus 1, and the pool at 1 is chosen to be 1 to the power n, u of minus n minus 1. We have it chosen the left-sided sequence because the ROC is going inward. The second possible region of convergence is in between the two circles whose radiuses are 1 and 2. In this case, we have a two-sided sequence. So if you go back here, and consider the ROC in between the two circles. For the pool located at 2, the ROC is going inward. So the term in time domain should be 2 to the power nu of minus n minus 1. Whereas for this pool located at 1, the ROC is going outward. So the term should be 1 to the power nu of n. So here, 1 to the power nu of n and 2 to the power nu of minus n minus 1. And delta of n is the same. The third possible region of convergence is that modulus z is larger than 2. In this case, the sequence should be right-sided, and we will get a term like 2 to the power nu of n plus 1 to the power nu of n. Okay, so this concludes part of for the inverse Z transform. In the next part of today's lecture, we will start working with the properties of the Z transform.